Hello everyone, I'm Himalay. This presentation is about our work on knowledge distillation called QuEST, Quantized Embedding Space for Transferring Knowledge. Knowledge distillation is the process of training a student network to achieve better accuracy by learning from a pre-trained teacher network. To that end, the student is trained with a distillation loss that guides it to mimic some aspects of the pre-trained teacher network. A common example is that of training the student to output the same softmax classification probabilities as the teacher. Those softmax probabilities are also known as soft predictions. Another very popular example is that of training the student to regress the teacher's feature map or some derivatives of those features, such as their attention map. The main intuition behind this line of work is that these features tend to encode useful semantic knowledge for transfer learning. However, naively regressing the teacher features might be a difficult task which over-regularizes the student, thus leading to a suboptimal knowledge transfer solution. This is because too much focus is paid on feature details, by which we mean the exact feature magnitudes of the teacher network. Those feature details are not necessarily important aspects of the teacher networks that need to be transferred. Furthermore, their behavior largely depends on the network architecture design and capacity that, in the case of knowledge transfer problem, are usually different between the teacher and the student networks. In this work, to ameliorate this problem, we propose a novel method that addresses the knowledge transfer task in the context of a specially dense quantization of feature maps into visual codes. Briefly, first we learn with k-means a dictionary of quantized deep features from the teacher network, which we call visual words. Then given an image, we use this vocabulary to assign each local features into the closest visual words. As distillation task, the student predicts these teacher word assignments using an auxiliary convolutional module. Let's see in more detail how the quantization on the teacher side is done. The purpose of this step is to convert the teacher's feature maps into teacher word assignment maps, which are used as the target for the student in our distillation loss. To that end, the assignment block uses a vocabulary learned offline with k-means on the feature maps of the teacher. The visual words of this vocabulary, which we call as the teacher words, are representative of the important visual concepts that the teacher learned to detect. So given this vocabulary, we generate the teacher word assignment maps by computing the Euclidean distance between the vectors in the feature maps and the teacher words, and then soft assigning each feature vector to its closest visual words by passing the negative distances through a softmax function. As the distillation task, the student has to predict the teacher word assignment map. This is done via the assignment predictor. The assignment predictor consists of one cosine similarity based 1 by 1 convolution layer with as many output channels as the vocabulary size. The convolution is followed by a softmax function with a learnable scaling factor that converts the activations to soft assignments over words. We want those predicted word assignments to match the target assignments on the teacher side. Both of those word assignments have the form of softmax probability distribution over the words. Therefore, we define the distillation loss as the summation over all the locations of the KL divergence from the predicted word distribution to the target word distribution at the teacher side. This loss is minimized over the parameters of the student network and the assignment predictor. In our method, the teacher's feature maps are essentially discretized into visual words. We include some examples of those visual words at the bottom of the slide where we see that they encode mid to high level visual concepts. So, by minimizing the KL divergence, Between the predicted visual word assignments and the teacher assignments, the student essentially learns to detect the same discrete visual codes as the teacher does. This way, the student learns to align its feature maps with those of the teacher network, both spatially and semantically, but without being forced to regress the exact feature details of its teacher. Differently put it, QuEST can be seen as a regression problem turned into a classification problem that is known to be easier to optimize and thus a more effective learning strategy. Further, if we see QuEST in relation to the KD method, QuEST also mimics softened classification predictions but in a spatially dense way over the teacher words, which represent much more numerous visual concepts than image classes. Now moving to the main experimental evaluation of our method against many state-of-the-art methods. We first start with model compression results, in which the student has lower capacity or number of parameters compared to its teacher. Here are the results of model compression on ImageNet dataset with ResNet34 teacher and ResNet18 student, which have the same ResNet architecture design, and ResNet50 teacher to MobileNet student, which are different network architectures. The tables compare top 1 and top 5 error rates on ImageNet validation set of the student network with various distillation methods. Our method, QuEST, outperforms the prior methods by a significant margin. We also test our method for model compression on CIFAR 100 dataset with several network architectures. The table is divided into two parts. In the first part, the teacher and the student have the same network architecture design, while in the second part, they are different. The proposed method QuEST achieves better accuracy than the other distillation methods, and in some cases, it even outperforms the teacher. We also test our approach for transfer learning scenario. Here the teacher is pre-trained on ImageNet dataset and the student with lower capacity is trained on MIT67 dataset. Further, to assess the performance on small training sets, we reduce the number of training images per class to up to 10. The top rows of the table show the results of student accuracy when trained from scratch on MIT67 and when the student is pre-trained on ImageNet and fine-tuned on MIT67 without using their teacher. Comparing QuEST with them on ResNet18 student and ResNet34 teacher, our method outperformed not only the training from scratch, but interestingly also fine-tuning, which is the popular method for transfer learning. Further comparing with other knowledge distillation methods, our method either outperforms the prior knowledge distillation methods or it is at par with them. We observe a similar outcome as before with ResNet50 teacher and VGG9 student. To conclude, in this work, we proposed a novel knowledge distillation method. Our method distills the knowledge through a quantized visual word space. Our simple approach improves the state of the art on knowledge distillation. We conducted several experiments to evaluate the proposed approach on various teacher-student pairs and datasets for the task of model compression and transfer learning. Thank you.